Hello, welcome to Maths Clinic series. Thank you for choosing Maths Clinic. And in Maths Clinic, all that we do is to help students like you to overcome mathematics and to see maths as one of the easiest subjects in this world. In this video, we are looking at calculus. Calculus to you as an SHS student, it is a topic in elective mathematics, but it is a whole course for someone in the university. Calculus can even be a program that somebody can model for the entire course or entire program in the university. Now, what is calculus? In ancient times, we will say that calculus is a Latin word which means a small stone or rock used for counting. People in ancient times did arithmetics with piles of stones. So they could add, they could subtract, they could multiply with piles of stones. And so a particular method of computation in mathematics came to be known as calculus. In modern times now, we will say that calculus, which is a branch of mathematics, it aims of focusing on limits, functions, derivatives, integral, infinite series. It is a study of how things change. One thing changes with respect to other. And so in these modern times, we look at calculus as a form of studying how things change. Now, here we are going to look at two basic major branches of calculus, and they are differential calculus and integral calculus. And so we'll take them one after the other. But before we do that, why do we need to study calculus? What is it all about calculus that everybody wants to go through? It's so important. We want to look at application of calculus before we take differential calculus and later pick the integral calculus.
Biologists use differential calculus to determine the exact rate of growth in a bacterial culture when different variables such as temperature and food source are changed. This research can help increase the rate of growth of necessary bacteria or decrease the rate of growth for harmful and potentially threatening bacteria.
An electrical engineer uses integration to determine the exact length of power cable needed to connect two substations that are miles apart. Because the cable is hung from poles, it is constantly curving. Calculus allows a precise figure to be determined.
An architect will use integration to determine the amount of materials necessary to construct a curved dome over a new sports arena, as well as calculate the weight of that dome and determine the type of support structure required. It is also used to design bridges and houses.
Space flight engineers frequently use calculus when planning lengthy missions. To launch an exploratory probe, they must consider the different orbiting velocities of the Earth and the planet the probe is targeting for, as well as other gravitational influences like the Sun and the Moon. Calculus allows each of those variables to be accurately taken into account.
A physicist uses calculus to find the center of mass of a sports utility vehicle to design appropriate safety features that must match to federal specifications on different road surfaces and at different speeds.
A graphics artist uses calculus to determine surface area, volume, and how three-dimensional models will behave when subjected to rapidly changing conditions. This can create a realistic environment for movies or video games.
This is a video I picked from YouTube, and I believe it has given you the overview of what calculus is all about. In fact, you realize that calculus has got so many applications. Everything that is made with curves, it came to existence because of calculus. Because calculus was able to use to measure curves and relations. Now let's look at what differential calculus is all about. So let's look at differentiation. What is differentiation or differential calculus? Differentiation is an operation that allows us to find a function that outputs the rate of change of one variable with respect to another variable. And so with differentiation, we'll be having two variables. For example, if I think of height and weight, is there any relationship between height and weight? Is there any relationship between speed and time or velocity and time? These are some of the things we are going to consider under differentiation. The process of finding the differential coefficient of a function, let's say if I have f of x, with respect to the independent variable x, is called a differentiation. And that's what other people can define differentiation. The differential coefficient of the function is also called the derived function or the derivative of a function. And I will explain that later. So now let's first look at differentiation from the first principle. Differentiation from the first principle. And we will start that by looking at the linear function or differentiating a linear function. This is a graph, a linear function, which is of the form y equals 3x plus 2. In fact, this is a graph of y equals 3x plus 2. And this is a linear graph. Now I want to look at the gradient of this graph. We know that gradient of a function is defined as m equals change in y on change in x. This is what we know as how to find the gradient of a function or a linear function or a straight line. We can calculate the gradient of this straight line by taking 2 points. For example, if I pick this particular point here, which is 1, 5, 1 and 5, and I pick this point, which is 0, 2, then I can find the gradient of this point. If I call this x1 and y1, then I can call this x2, y2. And we know the gradient is change in y on change in x. And so change in y, it means I'll have y2 minus y1, x2 minus x1. And by so doing, if I pick the y2, which is 2, minus y1, which is 5, to divide by x2, which is 0, minus x1, which is 1. And this can be calculated as negative 3 on negative 1, and the result will be 3, positive. Now, what it means here is that if I pick any 2 points on this very straight line, I'll get the same result as 3. What does that mean to us as we study differential calculus? Let's consider this table of values or this particular function that we have. In fact, the same function that we've been able to calculate its gradient, that's the function that we have here. It means that if I select some values of x, starting from negative 4 to positive 3, and I want to compute the corresponding values of y. So by the function y equals 3x plus 2, if s is equals to 4, negative 4, what will be the y value? And here you can see that if I put negative 4 here, I'm going to have 3 times negative 4, which is negative 12, plus 2 will give me negative 10. Then when I try for the negative 3, I'm going to have negative 3 times 3 will be negative 9, and plus 2 will give me negative 7. And when I do it for the negative 2, I'm going to have negative 6 minus a plus 2, which will be negative 4, So the final one will give us 11 here. Now we want to observe these two values critically. You see that the S values changes in units. -4 to -3 to -2 to -1, 0, 1, 2, 3, and it can go on and on and on. But what happens to the Y values? Y values changes as 3 units. You can see that from -10, they will go to -7, plus +3 will give us -4, plus 3 will give us -1, plus 3 will give us 2, plus 3 will give us 5, 8, and 11. So we can see that as S increases in units, Y increases in 3 units. So we say that the rate of change of Y with respect to X is 3. The rate of change of Y with respect to X is 3. Hope that makes sense to you. And so we can conclude by saying that the rate of change of Y with respect to X is the same as the gradient, because as S increases in 1 unit, Y increases in 3 units, and that 3 unit gives us the gradient. And as we said earlier on, anywhere you pick any 2 points on this very straight line and you find the gradient, you always get 3. And you can even try it and then pick any 2 points on this straight line, and you see that if you calculate the gradient, you always get 3. And so the conclusion is that the rate of change of Y with respect to X is 3, and is the same as the gradient of the line, which is 3. Now we want to look at differentiating a curved function. We've looked at differentiating a linear function, and we've seen that every straight line has got a constant gradient. That means wherever you pick any point on the straight line, you get the same gradient for it. And so straight lines have got constant gradient. What happens to curves? So curves like this, can we get a constant gradient? Is it that when I pick any 2 points from this particular line or a curve, I'm going to get the same gradient? The answer is no, because the gradient at this point will not be the gradient at this point. And we can prove that and see. So you can see that if I have this as a tangent, and I want to know whether this tangent will have a same gradient throughout the curve, you can see that it won't be the same gradient. Let me measure the gradient of this tangent. I'm using GeoGebra, and it's a very powerful tool for mathematics. Okay, so the slope of this line, or the gradient of this line, you can see that it is now -2.1. So as the gradient moves, you see that as the tangent moves, the gradient changes. So the gradient is not equal throughout the curve. And so it is very difficult to measure the gradient of a curve, because it rises at a point and falls at a point. And so we need to employ more technical mathematics to deal with gradient of a curve. And that is the reason for calculus or differentiation. Let's consider this curve of a function which is f of x. That is the red curve, is a function f of x. So f of x is the function, that is the red line has been drawn. And we want to look at the blue line, that is the PB line, as a secant. It's not a tangent yet, it's a secant. It's a line that crosses a curve or a circle. And then there are 2 points on the function f of x, which is the red curve. There are 2 points P and B. Now, if P has got S value here, which is x, okay, and its corresponding value is y, and I want to call that y as the function, which is f of x. And so here's f of x. In that case, this p is going to be called the point. The point is going to be called x, comma, f of x. That is for the p. If you consider the point b, also, we assume that the point b is having a point s plus 8. Now, I want to explain that to you very clearly. Let's assume that here is 2, and this point is 5. The difference of x and 5 is going to be 3. That is 2 and 5 is going to be 3. Then you see that if I say change in x means s2 minus x1. And if here is s2 and here is s1, change in s will be this. And so the change in s, I've called it h. And so if here is 2 and I want to get this point, I'll add the change in s plus the x, which is 2, to give me this one. And so you can see that here s plus h, which is 3, will give us 5. And so we see s plus h here. It makes sense. If here is x, and if you want to know the point here, it means you add a difference to it and you get a point here. Good. And so if that is the case, then the corresponding y value is going to be f of h, s plus h. If here is x and here is f of x, then if here is s plus h, then here will be f of s plus h. I think it makes sense. Good. Now, we want to find the gradient of this line PB. It's not a tangent yet, but we want to find the gradient. And we know that to find the gradient, we say gradient m is equals to change in y on change in x. And change in y, it means we want to find the difference of y values. And that will give us f of s plus h minus f of x. Because change in y means y2 minus y1. And this is the bigger number. So if here is 1, here will be 5 or 2 or 3. That means the bigger number minus the smaller number. And then the change in s is going to be the bigger number s plus h, which is this one, minus x. And this can be simplified as f of x plus h minus f of x, all divided by h. The reason is that this x minus x here will be 0, leaving out with only the h. And so to find the gradient of the straight line, which is the blue line PB, based on what we have here, we can see that that will give us gradient is equal to change in y, which is f of s plus h minus f of x, all divided by h. Now, if P decide to move towards B, if P is moving, the point P is moving towards B, the question is, what happens to the line, the blue line, the straight line? What will it be doing? And what happens to the difference of x2 and x1? That is the change in x, which is the h. What will happen to it? We want to demonstrate this one using the GeoGebra and see what will happen as P is moving towards the B. What happens to the h and what happens to the line PB? Now let's see what happens if P is moving closer and closer to the point B. What do we see? You see that here the P has got s value to be 1, and then that means the x is 1 and x2 is 7. The change in x and x2 is 6 because the difference between 1 and 7 is 6. And so as P is moving towards B, you see that the s value, which is supposed to be 6, is reducing. So let's see. You see that it's reducing because now if it is 1, it has moved to 2. The difference is what? It's 5. And as I move it to 3, the difference is what? 4. As I move it to 4, the difference is what? 3. As I move closer, I'm getting 2. I'm getting 1. I'm getting 0.1, 0.0, 0. Something. It's approaching 0. And when it is approaching 0, that means the change in x is getting to 0, that is the h is getting to 0. And what happens to the blue line? The blue line is also getting closer and closer and becoming a tangent. You see, it was a secant. It passes through the circle or the curve. Now, as it moves closer to B, the line blue is becoming a tangent. And when it becomes a tangent, then it means that the gradient of the tangent will be getting closer to the gradient of the curve. And so we will define again by saying that as P approaches B, H is approaching 0. And the blue line is becoming a tangent. I hope it makes sense. Look at the definition. As P is approaching B, H being the change in y, change in x, is approaching 0 as the line is becoming a tangent. I hope it makes sense now. So let's see what happens. So again, we see that as we did with the GeoGebra, when P is moving to B, then the H will be approaching 0, and then the line PB is getting closer or becoming a tangent. But we know that the gradient of the PB is given as m is equals to this. We've done that already. So now that the gradient of PB is now a tangent, then we'll say that its gradient now is becoming this. The limit as h is approaching 0, that means when P is going to B, h will be approaching 0, then the gradient f of x will be this. Our gradient is now going to be this. It means the gradient originally supposed to be this one. But because the P is approaching B and H is approaching 0, then it will be defined as limit as H approaching 0, then f of s plus h minus that is going to give us this. And so if P moves to B and h approaches 0, then our gradient is not going to be like this again, but it's going to be defined in terms of limit, because it will be as P is moving to B, h is approaching 0, and that defines limit. And this limit is going to be very close to change in y on change in x for a straight line. And change in y and change in x is now going to be defined as dy dx. We saw that every straight line has got a constant gradient. And this curve is not a straight line. But as we move P closer to B and the line is becoming a tangent, then the gradient is more or less becoming closer to the gradient of the curve. And so we'll say that when we take the limit of a gradient of a straight line, then the result will be the derivative of y with respect to x, which defines the gradient of the curve. That is what first principle is all about. And so in conclusion, we can say that if we take the normal gradient and we want it to approach a tangent of a curve, then we define the tangent as dy dx, which is equal to the limit, because it was the limit that made dy dx to look like change in y on change in x. And so dy dx is equals to the limit as h approaches 0 of the function f of s plus h minus f of s over h. And this statement is what we call the first principle of the differential calculus. And the dy dx is called the derivative of the function. The dy dx is called the derivative of a function. So the function is f of x. Sometimes you can write the derivative as this: f prime of that, or if it is y, we'll say dy dx. If it is f of x, we'll say f prime of x. If the function is called h, then the derivative is going to be defined as h prime of x. And that is the first principle. We'll take series of examples to understand this differential calculus. The first example we want to look at is this. From the first principle, differentiate y equals x squared plus 1. What it means is that you are being asked to find the gradient of this curve. And since there is a curve, its gradient is not consistent, or it's not a constant gradient. We saw that if it's a straight line, it's a constant gradient. And so for us to find the gradient of this curve, they want to find the tangent to a point on the curve. And at that point, the s value will help us to know the gradient. Okay, so let's sketch this curve and see how it looks like in original form, and then see the gradient of this curve. So I'm using GeoGebra to sketch this. So we are talking about y is equals to x squared plus 1. You don't need to do this every time. I just want you to understand the basis of calculus so that as you progress, it won't be like an abstract something for you. It will make sense to you. Now, this is the curve we want to find its gradient, or want to differentiate it. So the question is, at what point are we to differentiate this? When I put a point here and I draw the gradient or the tangent, I've changed the colors for you to see the difference between the two. Now, this is the gradient, the tangent to this very curve. Okay, so at what point are we to calculate the gradient? If you calculate the gradient at this very point here, where x is equals to what? Where x is equals to negative 2.52 is here. You can see it from here. 2.52. What will be the result of the derivative? And so we want to do that by calculating using the first principle. They will see. So in solving it using the first principle, the formula is this. This is the first principle formula. I'll give you two different formulas. This is the first one. dy dx, or the derivative of the function, is equals to the limit as h approaches 0, f of s plus h minus f of s over h. This function is the same as f of x, okay, because y is represented as f of x. And so what I'm going to do is that this equals to the limit as h approaches 0 of f of x. That means whatever I see x in the function, I'll replace by s plus h. And so I want to write the function x, and x will be s plus h all squared, okay, plus 1, then minus the whole function, which is f of x, so that will be x squared plus 1, all divided by the h. So I'm trying to write the function in place of this, and that is how the formula is going to be like. So this equals to the limit. I can't stop writing limit because I've not taken the limit yet. And this course, you will understand it better if you have studied limit of a function. It's a topic on its own, limit as a form of introduction to calculus. And so if you've not studied limit, you need to go back to limit and understand limit. Then you can come back to this and it will make sense to you. When I expand this one, I have x squared plus 2xh plus h squared plus 1 minus x squared plus 1, all divided by h. So let's move a bit back upwards. Okay, so limit again. Remember that you can't stop writing limit until you finish with the work. Now you can see that after the expansion, this will die with this, and then this one also will die. Sorry, that one will be the same. 1 plus 1 is 2. So I can write 2xh plus h squared plus 2. It makes sense that way, right? Oh, sorry, there is a mistake here. This x must be in bracket. This function must be in bracket because the negative sign affects the 2. So here should be minus. And so since here is minus, that means this would really die with this. I thought as much. And so that means these two will not come. And we have over h. Then again, we can say limit as h approaches 0. And I can factor h out from the numerator side. And I have this plus h all on that. And now this h also will cancel the h here. This will die with this. So we have limit, limit as h approaches 0. Then we're having 2x plus h. Now as we take the limit as h approaches 0 and we put 0 in place of this, which of course that's how we do limit, we have 2x as our result. And so the differential of y is equals to x squared plus 1. It means our dy dx will be equal to 2x. That is it. It means that if I put the point at anywhere of x, I can see the gradient of the line or of the curve. So let's interpret that here. We had 2x as our answer for the derivative of this particular function. So it means that if I choose to let s be equal to 0, you can see that here s is equal to 0 because the a is at 0, 1. And when s is equal to 0, what is the gradient? Maybe let's measure the gradient of the line and see. So I can measure the gradient slope of this line. And here you can see that m is equal to 0. Okay. And if I move the point to a, which is the point a to 1 at x-axis side, you can see it from here, our gradient is going to be 2. That means 1 times 2 is 2 because we say s is the function gave us 2x. And so if x is 1, then the gradient will be 2. Really, that is true over here. If s moves to, let's say, if s moves to, let's say, 2, our gradient becomes 4. So this is really confirming what we calculated for right now, that our gradient of the curve is 2x. And so whatever the tangent will be on the curve will determine the final value of the gradient of the function that was given as y equals x squared plus 1. And this is what first principle is all about. So we can take series of examples and solve them. This time around, without even drawing the curve, we can still use the formula to generate our gradient or our derivative. Example 2. Differentiate with respect to s the function this. We want to differentiate this function. Remember, it's a curve. Because the power 2 means a curve. Power 2, power 3, power 4, all was are curves. When it's power 1, then we see it's a linear function. That one is a constant gradient, so no problem. And so we want to find this. Now, using the formula dy ds equals limit as that, we will say that this is equals to, that's the dy dx is equals to the limit as h approaches 0. Now, we are writing the function 2. Whenever we see s, we put this function there. Because it's saying f of s plus h. So we are writing this function 2 into bracket times x. And x is s plus h. And it's squared, so we'll square this. Minus 3. So that is the function. We are done with this part. Then the whole thing minus f of x. And f of x is the whole of this function because we said that this one represents f of x. And so f of x is 2x squared minus 3. Then everything divided by h per the formula. And so this is equals to the limit as h approaches 0. The moment you stop writing limit means you are concluding. So the limit must always be there. Don't leave it. You leave it, it's wrong. So we expand this. So we have 2 into bracket. When you expand this one alone, we are going to get s squared plus 2sh plus h squared minus the 3. Then minus this will affect this to give you, sorry, so it will be 2x squared, then plus negative negative, so plus 3, all divided by our h. So we can now expand. So I repeat my limit. When I expand this, I'm going to have 2x squared 4xh 2h squared minus 3 minus 2x squared plus 3, all divided by h. Move it a bit up. Now this will be limit as h approaches 0. Now you can see some cancellation. This will die with this. This is minus 3 and this is plus 3, so they will also go out, leaving me with 4sh plus 2h squared on h. So I can still repeat my limit again. This time around I can factor h out, 4s plus 2. Okay, it makes sense that way, right? No, there's h here, all divided by h, right? Because when I take the h out, I'll have 4s plus 2h, because there are 2h here. So I take one out, I'll be left with h divided by h, and this will die with this, leaving me with limit as h approaches 0, 4x plus 2h. Now I can take my limit. So dy dx is equals to, now limit as h approaches 0 means whenever I see h, I can put 0 there. Then I have x squared 4x plus 0, and that becomes the final answer. Now remember that we can't put h as 0 into the h here, as we've not simplified to this far. Here when I put h 0 here, 0 here, 0 here, I'm going to get undefined. And per the lessons on limits, you realize that you have to go down until you get it to the simplified form before you can substitute a 0 in place of h. And so dy ds of the function given is equals to 4x. Example number 3. Here you have to find the gradient of the curve, and this is the curve using the first principles. You can pause this video and try your hand on this. Even though I'll solve this question, but I won't finish the whole entire solution. I'll give you a gist of it. So you try your hand on it first. Okay, so if you have your dy dx, then you have your limit as h approaches 0, then you now are going to write this function. Okay, sorry for that. So 3 into bracket, our x, and s represent this, to the power 2, plus 4, s again, and s represent this. Then we are done with the writing of the function in terms of this. Then minus the whole function, which is 3x squared plus 4x. Everything divided by our h. So the next thing we have to do is to expand. So by so doing, after writing our limit, as h approaches 0, we have 3 into bracket s squared plus 2sh plus h squared plus 4x plus 4h, that's by expanding the side of it, minus 3x squared minus 4x. Remember that this is minus affecting this. Then everything divided by h. So from here you can simplify everything. You simplify and then your final answer will give you this. So I want to give you the final answer to check whether yours answer is correct. So when you finish everything, you see that your dy dx will be equal to 6x plus 4. This will be your final answer. If you finish everything, you get this. I hope your answer is correct. Good. Now, example number 4. You have to, from the first principle, find the derivative of the function this. And this is also a curve. It's a curve. I hope you can try your hand on this. It's a little bit complicated because you have to do a lot of set work here. Maybe I'll give you a clue. Remember the formula we know already. So this will be equal to the limit as h approaches 0. We want to write this function, so we are going to have x, and x is s plus h. So everything under square root. Sorry for that. Okay, so everything under square root minus the function itself, all divided by h. And this time around, if you try to make the s look like half, it means you have to expand this one in terms of binomial expansion, and that will be a bit complicated. And so the best thing to do here is to rationalize the numerator instead. And remember your set. So to rationalize the numerator, you can say your limit as h approaches 0, s plus h, x over h, everything times square root of s plus h plus square root of x over the same thing, s plus h plus square root of x. This shouldn't be under the square root, so let me clean that part. And it's look like this. It ends here. And remember that when I cancel this, I get one and I get the same thing. So you expand this by that, and after the expansion, you can now simplify and you get your answer. Maybe let me go a little bit further for you to help you understand this aspect of the work. So limit as h approaches 0, this times this, they have the same root, so we can get s plus h. Then the same thing times that will give us square root of x times square root of s plus h. Then minus this times that will give us minus square root of x into bracket square root of x plus h. Then minus, remember, square root of x times square root of s will give you just x, all divided by, we have h into bracket root of s plus h. Okay, I shouldn't close the bracket here, so that I will say plus square root of x, then I'll close the bracket so that it multiplies everything there. You can see here that this will cancel this because they are the same. S root x, the root s plus h, the same root s plus h. And this x also die with this, leaving us with only h, which means that our limit as h approaches 0 is going to be leaving out with h on top over h into bracket square root of x plus h root of x, right? So that's what's going to be left. And here again, this h can die with this because this is multiplying, leaving out with the denominator alone. So the limit as okay, now when we take the limit from here as h approaches 0, whatever we see the h, we can substitute 0, and that will give us 1 on root of x plus root of x. So finally, our dy dx will be equal to 1 on, now root s plus root s will be 2 root x. So therefore, the function given, which was given as square root of s to differentiate, the result is going to be 1 on 2 root x. I think this is very cool. Let's take the other aspect of the first principle. Now, with the second approach, this is what you do. Normally, people refer that approach as Professor Alote's approach. Professor Alote has been a wonderful Ghanaian mathematician who has gone international level. Whereas whether this is true or not, I'm not very sure, but that's what I know. And this is what he did. Having y is equals to x square plus 1, what we do is that we apply change in y and change in x to both sides. So whenever I see y, I say change in y. Whenever I see x, I say change in x. And so I can say that here I'll add y plus change in y is equals to, here I have x plus change in x. And remember, because s is squared, then I'll square this one plus 1. And so when I expand the right hand side, I have x squared plus 2x change in x plus change in x also squared plus 1. So that is the expansion. Then I try to make change in y the subject. Change in y the subject, which means I have this squared plus 2x change in y s, plus change in s again all squared plus 1 minus y. Remember that minus y here will move to this side. That is y here will move to this side to become negative. But I know that y is equals to s squared plus 1. So I can write again this is equals to s squared plus 2x change in x plus change in x all squared plus 1 minus s squared minus 1. Remember, y was originally supposed to be s squared plus 1, and because the negative here, it will affect this one to be s squared, there will be minus 1. So here I can see that there are some terms that can cancel out. So I have y is equals to, this will die with this will die with this, leaving me with 2x change in x plus change in x all squared. Then I can divide both sides by change in x. So dividing here by change in x, here by change in x, here by change in x. Okay. So I have my change in y on change in x is equals to, this will cancel this. So I have 2x there and one of this will cancel one of this, leaving me with plus change in x alone. Now we learned that limit as change in s, which was initially as the h. So limit as this approaches 0 of the gradient is always approximate to dy dx. You get it? And so if I take the limit as change in y on change in x, it should be equivalent to dy dx. So dy dx is equal to the limit of this. So if I take the limit of this, the result should be equal to dy dx. And so I will say dy dx is equals to limit as change in x approaches 0 of 2x plus change in x. And this will be equal to, now whatever I see change in x, I put 0 there. And so my answer will be 2x. And that is what we had when we used the formula 1. And so they are the same. Go ahead and use this to solve other examples that we did and see whether you get the same answer. This is the second approach. Or so it means that when you are asked to find differential of every function using the first principle, you can use this particular approach or the one we did first. Any of them will give you the same answer, and any of them is accepted by any mathematician. So let's call this part 1 of calculus. Let's go for part 2.